Hi, Dr. Revis here. In this video, I will show you how to balance equations involving radioactive decay. Radioactive decay occurs when a radioactive isotope of an atom, an element, degrades to a lower atomic number atom or element with the emission of radioactive particles. The atom undergoes fission, also known as splitting. There are four particles that are discussed in this presentation. The alpha particles, which are represented by helium 4/2, beta particles 0/-1e, gamma irradiation 0/0, and 1/0 for neutrons. Shown here is an example of what a balanced equation looks like for the radioactive decay of uranium-236, which is formed by the impact of a neutron on uranium-235. Balancing radioactive decay means balancing the mass numbers, the superscripts, and the atomic numbers, the subscripts, on each side of the equation. To do this with the example here, we simply add up the left side for the superscripts, the middle equation, superscripts, and the far right equation, superscripts. And we note that they all balance out to 236, which represents the isotopic mass number for this species. We do the same for the subscripts, which represents the atomic number, and we know that it's 92. It's important to note that neutrons are represented by 1/0, which means that in order to balance this, we must multiply the number of neutrons times 3 and the atomic number times 3. In the case of atomic number, we get 0. In the case of the number of neutrons, we multiply times 3 and we get 3. And this is what the final balanced equation looks like. Let's practice this concept with plutonium-238, which has an atomic number of 94. Plutonium-238 can undergo radioactive decay to uranium-234 with an atomic number of 92. This leaves us with an unknown particle. To balance this, we add up the total superscripts and we observe that there are 4 short on the right side. So by adding 4 to the right side of the equation, we can balance the superscripts, which accounts for the isotopic mass. To do the atomic numbers, we know that we have 94 on the left side of the equation, and that means we must add 2 to the right side of the equation for it to be balanced. 4/2 lets us know that we have an alpha particle. Therefore, the balanced equation for plutonium-238 radioactive decay to uranium-234 occurs with the generation of an alpha particle, shown here. Let's practice this with iodine-131, shown here. In this case, we have another unknown particle. If we add the superscripts, we notice that we have 131 for the isotopic value on the left side of the equation. We also have 131 for the isotopic value on the right side of the equation. Therefore, we add a value of 0. For the subscripts, we start with an atomic number of 53. In order for that to be balanced, we must subtract 1 from the 54 for xenon on the right side of the equation. This gives us 0-1, which is a beta particle, which we write as 0/-1e. That gives us a a final balance equation shown here. In this example, we start with an unknown atom, an unknown element that has reacted with an alpha particle. To discover the unknown element, we add the superscripts, and we note that there are 13 on the right side of the equation, and there are only 4 on the left. For the subscript, which represents the atomic number, we have 6 on the right side of the equation and only 2 on the left side. So we balance these by doing the arithmetic. We discover 9 over 4. Next, we go to the periodic table to look for the atomic number with a value of 4. When we do that, we discover beryllium. Therefore, we have beryllium, isotope 9, atomic number 4, for a balanced equation shown here. Another example, we have uranium-235, which forms uranium-236, which undergoes further decay to an unknown element plus bromine 84 and 3 neutrons. So in this case, we're looking for an unknown particle and an unknown atom. To find that, we add the superscripts and the subscripts, and we look for the missing values. We do the arithmetic on both sides of the equations. On the left side, we discover a ratio of 1 over 0, which means that we have a neutron that's impacted the uranium-235. On the right side, we note a ratio of 146 over 57. The 57 is the atomic number of the missing atom or missing element. And we fill it in here, La, which means we have 146 for the isotope and 57 for the atomic number for lanthanum. That gives us a final balance equation shown here. There you have it, balancing radioactive decay equations.